Hi everyone, and welcome to this STEMfest in Space session. Really happy to be with you today. Today I'm going to be talking about designing rovers for Mars. So I work for a company called Airbus Defence and Space. It's part of the same company that makes Airbus aircraft, the planes that you might have flown on when you go on holiday, but in their space division. My name is Abbie Hutty, and I've been working for Airbus for 10 years now. And most of that time I've been working designing different Mars rover missions. So we have a site in Stevenage where we have lots of different facilities for our Mars rover programs. We've got a Mars yard, we call it, which is this thing that you can see behind me here, which is a warehouse full of rocks and sand so that we can test our rovers driving in a Mars-like environment. So driving over all of those obstacles and driving through sand and things like they might find on the surface of the planet Mars. And we also have a very special facility which is called the Mars Bioclean room, which is a really clean place where we can build our rovers in a sterile way to make sure that we're not taking Earth life with us. But I'll talk to you a little bit more about that as we go through my presentation. Why do we want to put rovers on Mars? And haven't we already got rovers on Mars? Well, both of those are very good questions. We have actually sent lots of missions to Mars in the past throughout history. But the more that we learn, the more that we want to learn. So we started looking at Mars through telescopes. And there was an astronomer in America called Percival Lowell, who actually made it his life's work to draw maps of what he could see through his telescope when he looked at Mars. And he looked at lots of different planets and other bodies in our solar systems, moons and things like that, and drew maps of those as well. And he kept seeing these lines on the surface. And both he and another astronomer called Schiaparelli, an Italian astronomer, saw these lines and thought that they might be something that's actually on the planet's surface. So Schiaparelli wrote in his notes that were published that he could see these canali, that was the Italian word, on the surface of Mars. Now, Percival Lowell tried to translate this into English and came up with the word canal, which in English has a very different meaning. In Italian, canali means a gully or a line in the sand. It could be natural or it could be man-made. Whereas in English, canals are made by humans. They're specifically built waterways designed to carry water and goods from one place to another. So Percival Lowell really was quite captured by this idea of canals on Mars in that sense of the word, and imagined all of these civilizations of Martian people carrying water from the polar ice caps that he could see down to what he imagined would be more desert-like lands, dry lands around the equator of Mars, and he decided to start mapping these. Unfortunately, we know now that actually there aren't any canals on Mars, and what he could see was actually a feature of looking through the telescope. So if you look through a telescope just right and the light shines onto the back of your eye, you can actually see a reflection of the back of your eye in the telescope. So what he was looking at was actually all of the veins in the back of his own eye, and that's what he was mapping. Unfortunately, he made it his life's work to map the back of his own eyeballs when he thought that he was mapping all of the canals on Mars. Anyway, this idea of canals on Mars was made quite broadly public. Lots of people heard about it, and lots of people became very excited about the idea of Martians, Mars people, and what those people would look like. And it spawned a whole generation of science fiction and books and films and television that still goes on to this day, thinking about Martians and what Mars life would look like. Since those times, we've sent lots of different missions to Mars. So our very earliest missions, like this one, Mariner 4, went past Mars. It didn't land on the surface, but just flew through space quite near to Mars and managed to take some black and white photos as it went past. And those photos didn't show any kind of canals on the surface, and people were quite disappointed that they weren't there. We then actually landed on the surface with a mission called Viking, and that was in the 60s. And these missions could take pictures of what they could see just in front of them. And this is one of the pictures that they sent back. And as you can see, that's very much a desert there. There aren't any obvious signs of civilization or life. And people began to think that actually perhaps there wasn't life on Mars after all, and definitely not little green people running around on the surface. Since then, we've sent a few different missions to Mars. All of them have been based on these ideas from previous missions that thought that there probably isn't life on Mars. Mars is just a big desert. But we've been looking to find out more about what is there on the planet. So are the conditions there possible to support our life if we went there? If humans travelled to Mars, could we survive? Has been really the focus of a lot of those missions. But those missions have found out some interesting scientific facts. So actually, we found some things on Mars that we didn't expect to find. And one of those things is methane. Now, on Earth, methane is caused by only two different processes. One of them is volcanoes, and you need the really, really high pressures and temperatures inside a volcano to create that methane gas. And another one is animals. So things like bacteria breaking down organic matter. They create methane gas, they release methane gas, and it happens in things like human digestive systems. All of the bacteria inside us break down the food that we eat and create gas, and that is methane gas. Now, we can see that there aren't any active volcanoes on Mars at the moment. We would be able to see the plumes of smoke from some of the orbiters that we have going round the surface of Mars and taking pictures. And we haven't seen any evidence of any active volcanoes. So that does mean that we're interested to know if the methane is actually coming from things like bacteria and organic things on the surface. The other thing is there's lots and lots of water on Mars. So when we first went there and we saw these really dusty, dry surfaces and deserts, we thought there was no water on Mars. But the more that we've looked, you actually find that it's frozen because Mars is very cold and it's below the surface. So it's not rivers and lakes on the surface like you find here on Earth, but actually the soil is quite wet and it's all frozen, so it's icy. But if you were to dig up some soil and heat it up, you'd find quite a lot of water content in that soil. So we know that that's one of the things that life on Earth needs to survive, is water. And actually there's a lot of water on Mars, which makes it more likely that life that was similar to Earth life would be able to survive on Mars. So we want to send a mission to look for life. That's what both of the missions that I've worked on so far in my life have been looking for. Actually, not just could we survive if we went there, or could future life survive if it went to Mars, but is there already life on Mars? Has there always been life on Mars? Are there Martians? And whilst we don't expect to be finding advanced civilizations with cities and canals and things like that anymore, we'd be looking for much simpler life, things like bacteria or other little tiny single-cell organisms. That's the kind of thing that we would be very excited to find, because it makes us think about our place in the universe very differently. If we know that there's life on other planets other than Earth, it maybe makes us understand what it means to be human, what it means to be a member of this universe, and how we should exist inside that universe, and what that means for us, what our responsibilities are as a member of that broader life outside of Earth. So, designing a Mars rover. Well, what do you have to do to design a Mars rover? Well, first you have to understand a lot about Mars and what environment it is that you're going to send this rover into, and what it's going to have to survive to be able to drive around and do its job. And one of the big things about Mars, it's actually really difficult, although it sounds not very complicated, is how very, very cold Mars is. Mars gets really cold. Down at the poles, like the North and South Pole of Mars, in the winter it can get to minus 130 degrees centigrade. much, much colder than it's ever been recorded here on Earth anywhere. And during the day, even in the summer, at the equator, where you'd expect it to be the hottest, it doesn't very often get much more than about 5 or 10 degrees centigrade. So the kind of temperatures that it is in the UK right now. And those temperatures can vary very significantly as well. So just from day to night here on Earth, it might be 20 degrees during the day, and then it will drop down to 10 degrees at night. So you've got a 10-degree difference between your daytime temperature and your nighttime temperature. On Mars, it can be as much as 100 degrees different from day to night, because the difference between being in the sunshine and being in the dark at night really makes so much more difference, because you're further away from the sun and that sunlight is so much weaker. So that is a real big problem for lots of things on our rover, especially batteries. Batteries work very badly in cold temperatures. They really like to be nice and warm, a kind of nice room temperature kind of thing. 20 degrees centigrade is about right. Computers and electronics really struggle at those very low temperatures. And even things like metals and carbon fibre and all of those kind of things behave very differently at those low temperatures. And actually, if they get knocked or bumped, they can break, they shatter like glass, rather than bending or flexing like they might do at warmer temperatures. So that means that we have to be very careful with anything that we're actually building our rover out of as well, to make sure that it's definitely still going to be strong enough. Now, we also have to land on the surface of Mars, and that's very difficult. You come in very, very fast into the top of Mars's atmosphere, and then you've somehow got to slow yourself right down before you hit the ground, so that you don't just dig a deep hole and end up broken and buried at the bottom of the hole when you've crashed into the surface of Mars. And then there's another thing that we have to think about, which you don't really ever have to think about on Earth, because Earth is just covered in life already. But we're looking for life on Mars. And that means that we need to be very, very careful about not taking Earth life with us. And that's two different things that you have to think about there. One is actually taking life. So taking bacteria or taking tiny organisms that might live on the human body, or fungi or other things like that. So we have to make sure that we clean our rover very carefully to make sure that there aren't any spores of fungus or bacteria or anything like that on the surface that are going to be transported with us to Mars. That then if they fell off and we picked up in our sample when we were looking for life and we found it, we'd think that it was Mars life, when actually it was just Earth life that we brought with us. The other thing that we have to think about is what materials we're building our rover out of, because the kinds of instruments that we use and we'll be looking for life with, or organic matter with, is the kind of thing that would detect, for example, that wood comes from a tree, or that kind of thing. So we need to make sure that when we're building our rover, we don't use anything that we would decide was organic, so anything that had ever grown or come from an animal or plant. And that means that all kinds of things that you would use here on Earth can't be used. Lots of different oils and greases that you might use to lubricate the wheels to make sure that they don't stick, all of those are organic. Lots of different paints that you might use to protect the surface, those are all organic. Lots of different plastics, things that you might use to wrap cables in to protect those metal wires and make sure that nothing electrocutes itself or short circuits against itself. All of those things are organic. So we have to be very careful that we're not using any of those things on our rover. Then there's another one, which is dust. And dust is a problem for a lot of different reasons. It sounds like such a simple thing, but dust on Mars behaves very differently to dust on Earth, and that's partly because the atmosphere is so thin and the gravity is quite light. And because Mars is very dry comparatively to Earth, and geologically very old, so there's not very many active volcanoes and things like that, there's a lot of loose dust around, and it's very, very fine dust. So all of the storms and wind and things like that over millions and millions of years have ground the rock down into tiny grains of sand, and then those grains of sand have broken down into tiny, tiny, tiny grains of dust, and it's really fine dust like talcum powder or something like that, very light and easy to suspend in the air. It goes in great big clouds. And actually, you have entire seasons of dust. So like we have weather, and different weather is more common in different seasons, they have a dust season on Mars. So all of these storms of dust can actually combine together, and you get a global dust storm. So the whole of the surface of planet Mars is covered in a dust storm all at once. And you can see that in these two pictures that I've got up on the screen. So both of these were taken by the Hubble telescope, the space telescope that's up in space near to Earth. So we pointed it at Mars twice, 3 months apart during this year. And in the first one, you can clearly see lots of things on the surface of the planet. So you can see the polar ice caps, like I mentioned, the North and the South Pole. You have frozen areas which are white, and we actually know that a lot of that is carbon dioxide ice as well as just water ice. So you have those poles and you can see them, and you can also see a lot of different features on the surface. So you can see impact craters and mountain ranges and things like that. And then on the picture on the right, there's just a brown blob, and that's because the whole of the surface of Mars has been engulfed in one of these dust storms. Now, if you're a rover driving around on the surface, you're using cameras to see where you're going, and if you're in a dust storm, it's just like being in a massive cloud of dust. You can't see where you're going, so you can't do anything. You can't drive anywhere because there could be any kind of obstacle or cliff or crater in front of you, and you wouldn't be able to see it. So you just have to sit tight and not do anything. But also, our rovers are solar powered. That means they're getting all of the energy that they need from solar panels on their backs, because there aren't any plug sockets on Mars. You can't just plug in to recharge. You need to be creating all of the energy that you need to carry on driving. And if you're in a dust storm like this, a really big, thick cloud of dust, the sunlight can't get through to your solar arrays, and so you can't create any more power. And if you run out of power and you can't keep yourself warm and you can't keep your computers going, the rover could basically die. That's the end of the mission. We wouldn't be able to start it up again. So we need to be very careful to make sure that we can survive dust storms like this. Now, some of the missions that we've already sent in the past have experienced dust storms like this, and this is a picture from one of those missions. So this is Spirit, which is one of the earliest NASA rovers that got sent to Mars in 2003. And you can see the dust has collected on the top of those solar arrays. So this is after the dust storm has passed. And you actually find that the dust sticks to your rover because it is so fine. Something like static electricity, just a tiny, tiny little charge on your rover, can mean that all of the dust clings onto the surface of the rover and it sticks really hard. And it means that you actually, even when the dust storm has passed, you still have all of this dust trapped on the surface of your solar cells, meaning you're not making as much power as you expected to. So we have to make sure that all of our solar arrays that we put onto our rovers are nice and big, plenty big enough to make lots of power, so that even if they have all of this extra dust collected on them, they still make enough power for the mission to keep on going. So just to kind of explain, you're not actually worried about the storm. It's not actually going to physically damage your rover because the actual wind speeds that you're talking about aren't that high, and there's not very thick atmosphere, so the wind isn't very strong either. There's not a lot of force behind it. It's not going to break the rover. What you're more worried about is where that dust is collecting. Is it collecting on the surface of your camera lenses? Is it collecting on your solar arrays? Is it lots of grit inside the hubs of your wheels that's going to grind and make those wheels break down? Those are the kind of things that we're worried about with dust. Now, this is a picture to show you what I mean by keeping our rover very clean. This is our Bioclean facility in Stevenage, and this is actually the ExoMars rover. So the one on the right is a model of the rover when we were still developing how the rover was going to be and what it was going to look like. We kept building, we call them prototypes. That means a type of model that you use to develop the next stage. And Bruno, which is the one that you can see there, and I went into the Bioclean room to see what it would be like in there once we were building the final rover. But actually, once you are building the final rover, which is the picture on the left, then you have to be a lot more careful about how clean everything is going in there. So you have to wash down all the walls with special cleaning fluids like bleach to make sure that it kills any bacteria or fungi or anything like that that might be in there. You have to have special filters on the air that are constantly pumping the air through and trapping any particles in the air. And everyone that has to go into that room has to wear these special suits to make sure that no grease from your hands or hairs from your heads or flakes of skin from your face or anything like that could fall off and get onto the rover and get carried to Mars with the rover. Getting onto Mars, so this is just a quick picture to show you how you might get onto the surface, and this is how we're planning on getting onto the surface with ExoMars, which is the first mission that I worked on. So you enter the atmosphere going really, really, really fast, hypersonic we call it, which means that you're much, much faster than the speed of sound. And at that point you're going so fast, and the forces working onto your capsule from the atmosphere are so strong that actually all you can do really is have a heat shield. So because you're going to get very, very hot from the friction of going through the atmosphere, you have to have a big, thick shield that will protect you from those temperatures and stop everything that's inside your capsule from melting. So we have a heat shield, and we go through the top of the atmosphere just using that heat shield to protect us from the temperatures. But actually that slows you down a little bit. And so once you've got a little bit of the way through the atmosphere, you can deploy a very, very small, very strong parachute. It can't be any bigger, otherwise it will just tear itself apart, but a very small parachute. And that will help to slow you down from what we call supersonic to subsonic, so above the speed of sound to below the speed of sound. And once you've slowed down to below the speed of sound, then you can get a much bigger parachute out and slow yourself right down. And at the same time, we tend to get rid of that heat shield. We say we jettison the heat shield. And then we can also fire rockets, little tiny rockets. So we call them retro rockets. And that means that they're pointed down towards the ground. And they actually help to slow down your capsule as you're moving towards the ground, but they can slow it down so much that you can actually come to a hover. And you hover above the planet's surface using your retro rockets. And then you can gradually shut those retro rockets down so you drop as carefully as possible onto the surface. And then we have shock absorbers in the legs of your landing platform, so that when you hit the ground, you get a bit of a thud, but it's not too hard. And then on ExoMars, the way that we're doing the next stage is that actually the rover is inside this capsule. So it's a little bit like a flower with all of the petals curled up around and the rover inside this capsule. And then once you're on the surface, all of the petals of that flower will open, and they're all like little ramps that the rover could choose to drive down onto the planet's surface. So we can pick which one looks like the safest way down and drive onto the surface. And we can also use some of those other petals for solar arrays to create power. So I want to talk to you a little bit about the two missions that I worked on in particular. So ExoMars is the first European Mars rover mission, and I worked on that for a very long time, 7 years, and it's nearly ready to launch. So ExoMars has the objective of looking for life, and it's actually going to do all of that itself. So on board the rover, we've got a full, basically, laboratory of science equipment that we can use. and the rover can take a sample, bring it back on board and do all of the science, all of the analysis that it wants to do to see whether there's any life inside that sample actually on board the rover. Now, just coming back a little bit, one of the reasons that we're particularly excited about Mars when we're talking about life in our solar system is because Mars is in an area that we call the Goldilocks zone. So that means that with respect to the sun, it's not too close to the sun that it's so hot that we think that any life would be just baked and couldn't survive because the temperatures are too extreme. But it's not so far away that the planet's so cold that we don't then think there'd be enough energy there to help any kind of life survive. So it's in the not too hot and not too cold zone. And so scientists like to call this the Goldilocks zone. And that's the area that we think is most likely that you'd find life. So of all of the planets in our solar system, with the exception of Earth, which is obviously right in the Goldilocks zone and has lots and lots of life, you've really only got Venus, Earth and Mars in that zone. And Venus, we know, is very hot and has lots of very nasty chemicals in the atmosphere. So we think that that would be very hard, both for life to exist and to send a mission to. So Mars is the one that scientists tend to look for life out of all the others. So this is our rover. We call it the Rosalind Franklin rover. And if I can just get the video to play. Sorry, it doesn't seem to want to play. Give me a second. Okay, unfortunately I don't think that's going to play, so we just have to talk about it. So this is what the Rosalind Franklin rover is due to look like. So you can see it's got big solar arrays on the back of it, and the solar arrays are how we create all of our power. It's got 6 wheels, which is how we drive around on the surface. And you've got a big neck, and on the top of that you've got a head, and on the top of that head there are cameras, and those cameras are like our eyes, and that's how we see to drive around on the surface. So we actually have eyes in a pair, like humans have 2 eyes, and that's because that's the way that you can tell how far away things are. We call it depth perception. And if you have 2 eyes that are actually set apart, you can look through one eye and you get a very slightly different picture as you do looking through the other eye. And by comparing those 2 pictures, you can tell how far away different objects are. And your brain does all of that automatically, but we've now been able to teach rovers and other robots and things like that how to do all of that mathematically and how to work out how big obstacles are, and that's how they'll be able to travel around on the surface and know where's safe and where's not safe. So we also have some science equipment on board. One of the really interesting things that we have is a ground penetrating radar, which I think sounds amazing. Basically that means it's a special type of camera that can look underneath the surface and decide what's there. So you actually have 2 of those as well, so that you can see what's there, but how far away that is as well. And that's the way that we'll be able to look and see whether there's, for example, a layer between rocks where there's a cavity with water in it or something like that, and that might be an ideal place for life to still be existing if it was there, nicely protected by a layer of rock over the top, but with plenty of water and other nutrients underneath the surface. So we're going to use our ground penetrating radar to look for good places to dig to look for life. And then we have a drill. Now this is the first time that we've really sent a big drill to Mars, and it's a bit of a game changer really, because we know that at the surface of Mars there's so much radiation coming from space and coming from the sun and things like that, and none of it is blocked out by, well, very little of it is blocked out by Mars's atmosphere, because the atmosphere on Mars is so thin and there's no magnetic field. So on Earth, we're very well protected from the radiation that's in space because our magnetic field helps to block off that radiation. It actually bounces off the surface of our magnetic field. And then the atmosphere, if anything does get through, blocks a lot of the rest of it. But neither of those things exist on Mars to the same degree, and so most of that radiation reaches the surface. And it's so extreme that actually, if there was anything alive at the surface, we think it would have been killed by this radiation. But not only killed, it would actually have broken down that life and damaged the life so much that we might not even be able to detect that it had previously been alive, it had previously been organic. So it'll actually deteriorate all of those molecules to the point that you won't be able to recognize them anymore. So we want to find something deeper below the surface where it's been protected, because the soil is very good at blocking out radiation as well. So we need to make sure that we're digging far enough into the ground to get below where that radiation is penetrated to. And that's what we're using our drill for. So our drill is enormous. It can actually drill up to 2 meters under the surface of Mars, which is about as tall as a very tall adult. And all that way, protected under the surface, is where we think we're most likely to find life if it was still existing on Mars today. So that's what we're very excited about deploying once we get to Mars. Now, you don't just build a Mars rover and have it work first time, unfortunately. Otherwise, my job would have been a lot quicker. So we've got a whole family of different, we call them prototypes or breadboards, and they're just different development models that we've used to learn more about how our Mars rover design works and to fine-tune and fix any details that didn't work how we expected or didn't work as well as we'd hoped. So we started off with Bridget, she was the very first one. And then we had Bradley and Bruno, they're actually twins, they're built to the same design, and we've used them to develop different parts of the rover as we've gone on. So Bradley has been used out in Italy, where they've been developing the drill and all of those kind of things, and Bruno has been used by us in Stevenage, developing what we call our autonomous navigation, but I'll come to that a little bit later. And then Brian is actually the most recent Mars rover prototype, and he's the one that we're using in our facility at the moment to do all of our testing of our final software to make sure that it will all work exactly as we want it to when we're on Mars. Now you can see that some of these rovers are actually quite skeletal. They've got just tiny thin beams holding them together, and they don't have the same body that the picture of the Rosalind Franklin, the final rover, that will have. And that's because we want these rovers, when we're driving around in our Mars yard, in our test facility, to behave like they will on Mars. And that means they need to slide down slopes and sink into sand and things like that, exactly the same as they will on Mars. But Mars gravity is only about 1/3 as strong as Earth gravity. And we don't have any anti-gravity devices. Unfortunately, we haven't invented those yet. So we need something that's only 1/3 of the weight that the rover will be when it finally is launched, so that it does sink in sand and slide down slopes in that same way as it will when it's only got 1/3 of the gravity acting on it. So we have to have these skeleton rovers for our testing and development in Stevenage, and then the final one will have a body. So Bruno here has got a body you can see that we've put on. It's not the real body, it's just to kind of visualize to give us an idea of how big that body will be, and all of the rest of them are skeletons. We've also got a really big team of people working on the rover. Now, we don't often get together. This is a picture we took for Christmas one year. You can see it's our Christmas jumper day, but I just wanted to show it to you to show you how many people it takes to design a Mars rover. There are lots of us, a very varied bunch. This is probably only about half of the people that work on the rover in Stevenage. a lot of people had gone off on Christmas holiday already by the time we had our Christmas jumper day. So there was at one point about 180 people in Stevenage working on this Mars rover mission alone. There are lots of other people at our site that work on different missions. And then there are other people all around the world that are working on the Mars rover mission as well. So people designing the drill, people designing all of the different instruments that go on board the rover, the cameras, people designing the landing platform and the whole module that will go down through the atmosphere and land our rovers safely on the surface, people designing the rocket. We estimate that overall it's taken about 1,000 different engineers working on this project to build this Mars rover. And we also had one very special helper at one point. You can't see his face, unfortunately, in these pictures, but Tim Peake, the British astronaut, when he was on the International Space Station, actually helped us in our development as well. So he controlled Bridget, our very first Mars rover, from space, and he actually drove her around in our facility in Stevenage, but all of the time while he was floating around in space on the International Space Station, just so that it could help us understand how we control that rover remotely and what it would be like to be driving a rover when you can't see the rover itself and you're a very long way away and you can't even see the surface where the rover is driving around. So we've had some very special help in our project as well. But when you're on the surface of Mars, the Earth is even further away than when you're in the International Space Station. So this is a picture that one of the NASA rovers took, and you can see the tiny dot of light in the sky is the Earth, and you can see the mountain range in the distance is the surface of the planet Mars. And when you're that far away from Earth, it's much, much harder to control your driving. And that's for one of the reasons is because even at the speed of light, so the speed that your signals, if you're sending electronic signals into space, the speed that they would get there can be between 4 minutes delay and 24 minutes delay. So just to send one command to your rover, it could take up to 24 minutes for that signal to be reached by your rover. And that means that if you're trying to drive by remote control, a bit like Tim Peake was when he was on the International Space Station, you have lots and lots of delays. You'd have to be very safe about all of your driving because you know that you can't go and pick your rover up if it falls over or slides down a cliff, that kind of thing. So you would have to order it to maybe take some pictures first thing in the morning and make sure that there hadn't been a sand drift or something in the night because of a dust storm. Make sure that you're safe to drive forward. So you'd send a command saying take some pictures, and it would take 24 minutes for your rover to get that command, take its pictures and send those pictures back, and that would take 24 minutes as well. So nearly an hour has gone past and all you've done is received those first pictures. Then you'd look at your pictures and you say, okay, I think we can safely drive forward a meter, and you'd send the command to drive forward a meter and then take some more pictures. And that would take another hour for that command to happen and for the rover to take its next set of pictures and send them back. And if you have to do that all the way across the surface of Mars, you really wouldn't travel very far in the amount of lifetime that your rover is expected to have. So we thought about this very hard, and we've actually developed a very special set of software that helps us to allow the rover to make its own decisions about where to drive. So we call this autonomous navigation. It means it's navigating by itself. And that means that it needs to be able to ask a number of different questions in sequence. So first of all, it needs to know where it is to start with, and we call that localization. Where are we? And we can answer that question because we've got satellites going around Mars and taking pictures, and actually our rover is big enough to see from those satellites. So we can take pictures and they look like a map with a tiny, tiny rover in the middle, and you can see where that rover is. And the next thing that we need to know, though, is what are the obstacles like actually around the rover. So that's called perception. So it has to be able to see in much more detail than those satellites can see from space what obstacles are there around it and how big they are and whether those will be safe to drive over or not. Then you have to make a decision about how you navigate through those obstacles. So how you pick a path, pick a safe route through those obstacles. And then you have to actually drive that route and make sure that you continue to drive the route that you're expecting to. And if you actually get, for example, your wheel stuck against a rock and it's spinning but you're not going anywhere, you need to be able to work that out and correct for it somehow, either by stopping and driving a different route or by putting more power into that wheel so that you can climb over that obstacle, to make sure that you can keep driving safely where you expect it to go and that you're not just sliding down a slope in an uncontrolled way that would lead you into danger at the bottom. So we spent a lot of time and energy and brain power in making our autonomous navigation software, and that's one of the big developments at Stevenage. So to do that, this is a little bit a taster of what we've done. So you take pictures with the cameras at the top of your mast, and you can see that the 3 pictures here are slightly different. You can see some of the same rocks in these 3 pictures, but from different angles. And we use computer software to combine the information in each of these pictures to work out what we call an elevation map, which looks a bit like this. And that shows you where all the slopes are and where all the rocks and obstacles are in front of you and how big they are, how high they are. And once you've worked that out, you can then categorize each of those obstacles and slopes into different levels of risk. So we know that if it's a nice, flat, smooth terrain in front of you, it's a very low risk to drive over it. You're probably going to be safe. But if there's a really big rock or a really steep slope, those are much higher risk. And so we can work out what level of risk our rover is happy with. It's definitely safe to go over. And we can put big blobs of stay out zone into the computer programming that says, this isn't safe, don't go over this, you have to stay away. So we start to build up maps that look like this. So all of the black area here is things that we haven't seen yet. All of the blue is the edge of where we can see. So you don't want to drive too close to the edge of where you can see, just in case there's a really big obstacle just out of view. And then you've got the white blobs are things that we know are too big or too dangerous to drive over. And they've got little grey kind of bubbles around those, which are the edge of that danger zone. So you draw a little line, and you can see the little black line there on the screen, which is the safe route for your rover to drive through those obstacles in front of it. And that's 2 meters long. And it drives that 2 meters, and then it stops and it takes a new set of pictures. And it does exactly the same thing again. And then you get the next set of pictures and you can plan your next 2 meters of path. And now you can keep doing that process all the way across the surface of Mars until, in this case, you could get to the corner of our Mars yard. So you can see there are 2 big walls at 90 degrees to each other, a nice square corner up in the top right there. And that's because we've driven into the corner of our Mars yard. And you can do that right the way across the surface of Mars. So you start in one place and you can tell your rover where its target is. And it doesn't have to be able to see the target. It can be up to 2 days drive away, but it knows where it is in relation to where it's starting. So it knows that it's maybe 200 meters in that direction. And it would just keep planning a path, heading in that direction, and picking its way through until it gets there. And then it will phone home and say, right guys, I'm here. What do you want me to do now? Are we going to do science? Are we going to do more driving? And the scientists will have worked out what we need to do next to our mission, and we'll send those commands. So that means that the rover travels much, much, much more of the time than it would than if it was just being driven by remote control, and you can cover much more ground and get to much more interesting science sites during the lifetime of the rover. Okay, so the next thing that I wanted to talk to you about is my latest mission. So we've built ExoMars now, it's very nearly ready to launch, and I'm working on a new mission which is called Sample Fetch Rover Mission. And that's part of a much bigger program of missions called the Mars Sample Return Program. And that's a partnership between NASA, the American Space Agency and ESA, the European Space Agency, to build a sequence of missions which will actually bring a sample, or lots of samples, from Mars back to Earth. Now, ExoMars is analysing everything that it will sample on board, and it's got all of its own instruments there to be able to do that. But there's a limitation on how accurate those instruments will be, just because they've got to be very, very small, compact instruments to be able to fit on the rover in the first place. And we would have much more sensitive instruments here on Earth when those instruments can be really big microscopes and spectrometers and things like that, things that take up an entire room or a laboratory here on Earth, and be much more sensitive and much more likely to pick up those very delicate signals that mean there is life. So this mission takes the different approach that actually we need to bring those samples from Mars back to Earth to be able to do the analysis here on Earth with all of our special equipment. And a bit like when we brought back the moon rocks, when astronauts first set foot on the moon, those moon rocks are still having different instruments fired at them today, because we develop more instruments, or we develop more sensitive instruments, and we can actually do more analysis on those samples than we could when we brought them back. And we hope that the same would be true about any samples that we brought back from Mars. So you need a lot of different complicated missions to be able to bring something back from Mars. You need to be able to launch into space in the first place on a rocket. You need to be able to travel across to Mars. You need to be able to land safely on the surface of Mars, and you need a rover that's then going to drive around on the surface to those interesting science sites and collect those samples. So actually all of those things we've got happening already. So there's a rover called Perseverance that NASA launched in July of this year, and that's on its way to Mars, and that's the first rover in the Mars sample return program. So that's going to drive around on the surface, and it's going to pick up samples. So this is an artist's impression of what that will look like, driving around on the surface and taking little samples. It's got a drill. It's not as big as ExoMars is. It only drills a few inches into the surface. But because we'll be able to analyse those samples with much, much more sensitive equipment, we're hoping that that will be enough for us to be able to detect signals of life if it is there. So once it's collected those samples, it will seal them into special little containers called canisters. And those will be left on the surface of Mars so that it can drive onto new places and keep collecting more samples. So then we need to send another mission to collect them. So we have the Mars Sample Return Lander, which is due to launch in 2026, and that's where my rover comes in. So a little bit like ExoMars, it has a big heat shield on the front and will travel through the atmosphere and down to the surface in this pod. And then when it gets to the surface, it will use its retro rockets to hover above the surface and to lower itself down to the planet's surface. And you can actually see on the top of this mission, you can see the wheels there of the rover that I'm working on. So it's actually upside down at the moment. On the top of this landing platform is our rover, all packed up, safe for the journey. And then when we get down onto the surface, the lander will have some solar panels that it will deploy so that it can start getting power. Our rover's still on the top of this landing platform, but it will get turned up the right way and put down onto the surface of Mars, and then it can drive around and collect all of those sample tubes that have been left there by Perseverance. So that's the rover that I'm working on at the moment. And we're using all the things that we developed from ExoMars to help us to design a more efficient and a more compact and a safe rover, with all of the same kind of autonomous navigation systems and things like that that we've already developed. So once we've collected all of those samples, we'll bring them back to the lander and load them on to a special capsule that then will be launched up from this special platform back into space. So it's a little bit like a missile. It's not very big, but a tiny little rocket containing a football-sized container full of samples will be launched into space. And once it's in space around Mars, it will rendezvous with another mission. So there's actually going to be a mission that again is being built in Europe, which will be the Mars Earth Return Orbiter, which will pick up that sample, that football of little sample tubes, and it will capture that in space and put it inside its body, and then it will drive over from Mars back to Earth orbit. So it will bring that sample back very close to the Earth, and once it's inside its special little landing capsule, it will drop it down to the surface of the Earth in a specially selected location where scientists will be able to go and retrieve it. And then it's all nicely boxed in, lots of different layers of sealing to make sure that it doesn't get contaminated with any Earth life. And we bring it into one of our very special, very clean facilities where we've already cleaned it down and made sure that there isn't any contamination. And so anything that we find in our samples really is something that's come back from Mars. So that's what I'm working on at the moment. Another Mars rover mission, and one with a very different approach to finding life on Mars. But both of them have that objective, and I really hope that in the next 5 or 10 years, once we've got the results from those missions, we'll be able to answer that ages-old question: are we alone in the universe? Is there life elsewhere from Earth? Are we Martians? One of the questions that scientists would love to know the answer for is actually, did life start in our solar system here on Earth, or did it start somewhere else? And one of the theories is actually that life might have started on Mars, and then some kind of asteroid impact or something like that might have blown a chunk off of Mars, and it might have landed on Earth. And that actually might be where all of the life on Earth evolved from. So you and I and everyone else here on Earth might be Martians. We would find that out from looking at the life on Mars and finding out how similar it is to the life that we recognise here on Earth. So all of these really exciting questions that we have to answer, and I'm really looking forward to finding out the answers to those, and I really hope that happens in all of your lifetimes and you get to see it as well. So thank you very much for listening to me today and hearing me talk about the Mars rover missions that I work on. It's such a shame that I can't answer all of your questions. I hope you have lots, because that means you've been thinking about what you've heard. So please do look into it more, do some research, look it up on the internet, ask your teacher, ask your parents, and I hope you enjoy carrying on learning about the fascinating topics that there are in the space industry, and my personal favourite, Mars. Thank you very much for your time today, and enjoy the rest of your day.